Good afternoon, professors, students, and friends. My name is Fuqun, and I'm coming from the Department of Mathematics. Today, I would like to share with you a very important and also exciting research programs that I have made during my MPhil studies in CUHK. This is actually a collaboration with Professor Yating Zhou from University of California, Riverside, and also my supervisor, Professor Jun Zhou. So for the title of today's talk is called a stable and fast direct sampling method for computerized tomography. So I guess for the audience today, the background is quite diversified. I will mainly give you some kind of motivation and ideas behind our algorithm. I will not really go into lots of mathematical details. So in any case, you are interested in the mathematical details of those algorithms, please feel free to ask me questions. Okay, for today's outline, first I will introduce what is computerized tomography. I guess computerized tomography is one of the most popular imaging technique that we can see in real life. For everyone, I guess we have seen something like CT scan in the hospital, and also we have seen see the application of CT scan in the security checks or in the fraud detection. One of the biggest problems for the CT scanning for the numerical algorithm to recover the data from the CT scan is the measurement data we collected is usually quite noisy. And sometimes we only have very few measurement data. Because you can imagine, if we do the security check in the subway station or in the airport, it's hard to get some very accurate measurement data. So in this case, our goal in this project is to develop some kind of algorithm that can work stably under limited and noisy measurement data. Basically, we are trying to combine the advantages of two category of path method. The first category is fast, but it's not stable under noise. For the second category, although it's quite stable under noise, but it takes really long time to compute. So we are trying to have these two advantages together. So now let's formulate the problem into some kind of mathematical setting. Basically, what we are trying to do in here is we are trying to recover some function f. F here is we can just imagine this is a good function. It's integrable. So we are trying to recover the function f from the random transform. The random transform here is just the measurement data we get in the CT scan. So this is the equation, 1.2. So basically what we are trying to do is to reconstruct the target function f from the measurement data from the random transform. Now we just reformulate our inverse problem a little bit so that I can explain our motivation or the idea easily. Basically, we can reformulate the original problem associated with the CT scan into the equation 1.4. Basically, in this case, our reconstruction is equivalent to recover the target function f from the integration between the target function f and some kind of kernel function. For the kernel function here, we call it fundamental solution for an operator, and this kernel function is 1 over the distance between 2 points, x and y. Basically, our ultimate goal here is to trying to recover f from this kind of integration. So now we will begin to construct our numerical method. Basically, this kind of direct sampling method, or referred to DSM, is some kind of numerical method that has been developed by our research group for almost 10 years. The general idea for this type of method is we are trying to solve some kind of inverse problem because we have measurement data and we are trying to recover something from the measurement data. We call this is an inverse problem. So we are trying to solve the inverse problem in some kind of direct way. Because in general, we can imagine for some kind of, if we would like to solve a system like AX equals B, if there is a lot of noisy data in the vector B, it's quite unstable to recover something. So we are trying to do something directly. So when we can apply this kind of idea in some inverse problem. So now we will see if the inverse problem under consideration has two properties. The first property we call fundamental property, the equation 2.1. You can see for the equation 2.1, this is just the 1.6. So we see this inverse problem has this kind of property. And the second property we call the almost orthogonality property. For this property, we claim if there is a set of probing function, eta, and eta is associated with a probing point inside the sampling domain. So if the coupling between the probing function eta and the Green's function or the fundamental solution is something like a dirty distribution. When we are talking dirty distribution, it's something like infinity, 1 point, and 0 in all other places. So if this coupling gives us something like a dirty distribution, actually we can recover the target function by the coupling between the measurement data and the probing function here. So now our task is to define something like what is the coupling is, the bracket in here, and also what is the probing function. Because we see our inverse problem has the first property. So here is a list of works about this method. So it has been developed for almost 10 years by the research group of Professor Jun Zhou. Now, before I introduce what kind of derivative, what kind of coupling that we would like to choose, I would like to present you some kind of other motivation. For the equation 2.3, actually this is an exact inversion formula for the Radon transform for the CT scanning. Actually, you can see here, although we can use this equation to recover the target function, there are two problems for this formula. The first problem is we can see we actually apply the Laplacian operator on the measurement data. But you can recall that Laplacian operator is actually some second order differential operator. So it's very, very dangerous. We apply a differential operator to some kind of noisy data. And there is a second problem is we can see this function jz actually is 1 over the distance between x and z. There is a singularity for this function. That is some kind of point with the infimum, with the infinity. So although as a mathematician, we are handling with infinity a lot, but in reality, there is no such a thing. We need some kind of finite value. So since Laplacian is unstable, we choose some kind of fractional Laplacian here. We choose Laplacian order 0.5, 0.4. So this is the first thing. This is the coupling that we choose. We choose some kind of fractional Laplacian and some L2 inner product. Then for the second part, since we think there is a singularity associated with the original function jz, so what we do? We remove the singularity. So you can see from the definition 2.6, we actually remove the singularity of the original function. However, there is also a problem. You can imagine that if we remove the singularity, somehow the accuracy or the sharpness of the reconstruction will be weakened. So in this case, we actually choose a larger exponent for the probing function, because originally you can see here is only the exponent is 1. So here we actually choose the exponents to be n plus 1. This is a way that we can improve the sharpness or the accuracy of the reconstruction. Now this family is simply the probing function that we choose. So finally, we formulate something. So for here, this is simply the coupling between the probing function and the measurement data. And we use this guy to recover the target function f that we would like to recover. So this is the final algorithm that we get, so-called direct sampling method. Now the third section for today's talk is I would like to justify or give some kind of convergence result and stability result for the method that I just proposed. The first result is a convergence result. Actually, we can show that the coupling between the measurement data and the probing function, when h goes to 0, h here is the distance between two detectors in the measurement. So as we get lots of detectors, as we get more and more detectors, actually we got the exact function finally. So this is a convergence result, and also quite surprisingly is this convergence is uniform, because for each point inside the domain, we got the same convergence rate. The other thing is about the stability, about how our method improve the stability of our reconstruction. Because we can recall that in the field of signal processing, if we have some kind of noisy measurement data, or if we have some kind of noisy data, we would like to apply a low pass filter to the measurement, to the data, and then the data can be improved. We got some kind of smooth data. And surprisingly, we finally found that although our primary motivation is not to design a low pass filter, but we just found that our probing function is actually something like a low pass filter. So this kind of understanding towards our algorithm actually shows how our method improves the stability of the reconstruction. Then for the third part is actually we can compute the variance of the reconstruction by assuming that the measurement data is polluted by a Gaussian noise. And in this case, if we define the variance of the reconstruction in this way, we can show that the variance actually depends on the gamma. Gamma here represents the order on appellation. So as we have a smaller order appellation, our reconstruction also becomes more stable. So this actually corresponds to our initial motivation to choose some kind of lower order operator in our method, but not the form appellation. So basically, our method is, from the perspective of computation, our method is actually very fast. It's O(n) log n flops. So it's actually it's the fastest method that we can see in real application, and also it's fully parallelable. So this is also very important because we can evaluate our reconstruction result for different points independently. Now I will give you two numerical experiments regarding our method. So basically, for the first experiment, we examine the case that there is a additive Gaussian noise or white noise or noise in the normal distribution in the measurement data. So basically, we found that the L2 error of our method is only 1/2, a little bit less than 1/2 of traditional method. And also for this case, we assume that we only have very, very limited measurement data, only 18 projections. And in this case, we found the error of our method is only 1/3 of traditional method. Basically, the method FPP is the most popular one in real applications now. Thank you very much. Any questions are welcome.
Thank you very much. So questions are welcome. Any question from our Zoom audience? You may type your questions in the chat room. All right. Any question from the audience in the venue? All right. First song, please.
Thank you. I think this you present a very important problem in the application and also on the mathematical development. So take this imaging as a real-world problem, right?
Yeah.
This is a broad application, and yet, as you correctly said, this noise is really important.
Yeah.
So what I like to understand is the fundamental thinking in this direct sampling method. What is the principle that make this method better than others in the so-called direct sampling method? I see the mathematical formula, but I'd like to know the principle that the difference in this method that make this method more sensitive and more easier to remove the noises?
Yeah, I see. Very good question. Thank you very much. And I think there are two perspectives or two points that I may raise. For the first point is actually, like I said, in this slide, we're actually trying to solve some kind of inverse problem directly. We're trying to avoid some kind of, because if we do the inverse problem, like we sometimes it involves to compute the inverse of a matrix, and we avoid this procedure, so it makes our method more stable. This is the first point. And the second point, actually, we have some kind of coupling. So what do we mean by coupling? Coupling here is we do integration in some kind of measurement surface. So if we do the differentiation, this makes the data more irregular. But if we do integration, we actually make something smoother. So this is another reason that it can make our method more stable.
So what I was also trying to understand is, for example, noise always come in irregular way, whereas if you design the mathematics, that you can recognize that these are irregular signals, therefore you can remove it, or is it that you design the method to maximize what you believe to be the important signal? Maximize that.
The later one. Yeah.
Okay. All right. Thank you.
Thank you very much.
Good afternoon, everyone. I'm greatly honored to be here and present my work with all of you. Thanks for the introduction. So the title of my talk is With Galerkin Method for Electrical Impedance Tomography. This is a joint work with my supervisor, Professor Jun Zhou. My talk would consist of 3 sections. In the first section, I will introduce what is electrical impedance tomography problem. In the second section, I will introduce the weak Galerkin method that we would use to solve the forward EIT problem. In the third section, I will present the convergence analysis that we carried out for the inverse problem, and also I will present some numerical experiments. So to start with, what is an electrical impedance tomography problem? The objective of such tomography problem is to estimate the unknown internal physical conductivity from the currents and the noisy voltage that we measured on the surface. Just as an example, we check this picture. The experimental setup is as follows. First, we attach a set of electrodes around the surface of that concerned object. Then we would apply some currents through this electrode. Then we can measure the result electric voltage from this electrode. We would conduct this process for several times until we have sufficient information to do the reconstruction of that conductivity. So as a typical implementation, once we attach the electrodes, we collect the voltage, and then we have the tomography of its conductivity distribution. And we may also have how the impedance changes over time. This EIT problem is difficult as it is nonlinear and ill-posed. By ill-posed, we mean the reconstruction is highly unstable with respect to the boundary measurements. Just it is the same kind of problem that Fuqun just introduced. So therefore, to deal with such ill-posedness, we need to find some regularization method. Previously, there has been Newton's regularization, factorization method, Tikhonov regularization method, and so on. In this work, we would use some regularization method based on bounded variation, and we will discuss it later. So to start with, I will give the mathematical formulation of this EIT problem. We will take a 2-dimensional problem as an example. The concerned object is this omega, and we'll use gamma to denote its boundary. We'll use E1, E2 to EL to denote the electrodes that we attached around the surface. Then we use this system of partial differential equations to describe how this electromagnetic field would form. That is, given the conductivity sigma here, given the induced current I here, we can use this system of partial differential equations to solve this pair U and capital U. This U is the interior potential. This capital U is the voltage we collect from the mesh from the electrodes. Here we use this H to denote the product space of U and capital U because we need to solve them two together. To solve this forward problem, we need to, if we want to use the finite element method that some of you might have been used it, for the finite element method, we need the variational formulation from the PDE. This is equivalent to the PDE and it's derived just using the integration by part and plugging the boundary condition that we have. This would give us this forward operator that is from the conductivity sigma and the induced current I, injected current I, we can map it to the pair U and capital U. Previously, by Bunty, Ying, and Petermans in 2012, we already have that this forward operator F is continuous and it is uniformly bounded. That makes it a well-posed problem as a forward one. So now we can move on to the inverse problem. It is an inverse process of the forward problem I just mentioned. That is, we have the noisy measurement of capital U and we have the current I. We want to reconstruct the unknown conductivity sigma. And we allow for some noise here as a noise level of delta. The regularization method we used is based on this bounded regularization. Some traditional choice of regularization might be the H1 functional. However, in this problem, we want to reconstruct the conductivity that is only piecewise regular, and it might have sharp, well-defined edges. It is discontinuous, and it might have possibly large jumps, and we care about these jumps. Therefore, we cannot use. It would be more suitable to use the bounded variation regularization. The definition is as follows. It is in a dual sense. And use this definition of bounded variation, we can write down the bounded variation space and also the admissible set A, where we will find the conductivity from this set A. It should have lower and upper bound and also bounded variation. So now we can present the minimization problem where we actually recast the reconstruction problem as this minimization problem. We find the sigma that minimizes J. The first term is the misfit function between the U and the measurement U delta. The second term is the bounded variation regularization. We use this alpha to compromise these two terms to ensure the best reconstruction. So mathematically, we prove that there exists at least one solution to the minimization problem. And also, with the help of this added bounded variation, we have that this minimization problem is stable with respect to the noisy measurement. Now we will move on to the second section about the Galerkin method. What is Galerkin method? It is different from the traditional conforming finite element method in the sense that it used weak partial differential operators. It is the partial differential operators would be generalized as some distribution that is over the space of discontinuous functions that include boundary conditions. For example, take gradient operator. As an example, from Green formula, the gradient operator should have this equality. Then we define something called weak function. That is, it is a pair V0 and VB. Plugging V0 and VB into the right-hand side of this equality, then they too would give the definition of the weak gradient of the weak function here. Then we can patch in this finite element space defined on each element together with the same value VB on the edge that two elements would share. In this way, we can define the finite element space on this whole domain. Now we can actually write down the weak Galerkin formulation. Take the ERT problem as an example. Recall that for the forward ERT problem, we get this variational formulation. Now we use weak Galerkin method. We would replace this gradient as weak gradient, and we would use those weak Galerkin finite element space to approximate the solution U and capital U, just like this. Just some replacement. However, we need to add this stabilized term as V0 and VB should not be so far away from each other. So we add this S term so that this discrete version of the variational formulation is stable and solvable. For the forward solver, we have the following error estimate. That is, in this induced norm H, we have the convergence order of H square. However, in the minimization problem J we just mentioned, the minimization is over the L2 norm of capital U. Therefore, we also need to prove this theorem on the convergence of this capital U in L2 norm. Finally, we can present the convergence analysis of the minimization algorithm I just mentioned. So this is the discrete version of that J. We use this UH sigma H solved from weak Galerkin formulation. And this is the discrete form of the B-wave functional I just mentioned. The convergence analysis of this algorithm consists of 3 steps. First, we prove that this discretized version JH also has at least a minimizer. And it is just as the continuous J, it is stable with respect to the noisy measurement. In the end, we prove that like sigma H star be the minimizer of those JH, then this sigma H star has a subsequence that would converge in L2 to a minimizer of the continuous minimization problem J as the mesh size goes to 0. And that is the end of the convergence analysis theoretically. When we actually implement this method, what we are really going to solve is the minimization problem JH. And this would involve the fast iterative shrinkage thresholding algorithm. That is because the B-wave term I just mentioned, it is not differentiable. It is convex, but not differentiable. That means Newton's method or any other gradient descent method are not working here. And we need to use such kind of thresholding algorithm. This algorithm that we use was proposed by Emil Beck and Mark de Bolle in 2009. It is initially mostly for imaging processing, etc. And the key concept we use is proximal map. In each iteration, there will be 2 previous steps information needed, and the key concept is here, PL proximal map. And PL is calculated using this FGP algorithm. So now we are ready to present some numerical results about our solver. For the forward solver, assume that we have this sigma equal to 1, and the convergence result is given here, which sees the convergence in the induced norm and also in the L2 norm of order H square. Now for the inverse problem, assume that for very simple case, when the true conductivity to be reconstructed is a linear one, then we have this sigma H star would converge to sigma in L2 norm in this convergence rate. So now that is the tomography. When the sigma to be reconstructed are continuous and not linear like this, the second figure shows our reconstruction using the exact measurement of U. And the third figure is a reconstruction using the measurement with noise level delta. You can tell that this reconstruction captures the location and the height of the true conductivity very well, and it is stable as this second and the third figure are not that different. For more difficult case, when the true conductivity to be reconstructed are these there are two obstacles, they are very discontinuous and separated to each other. We have our reconstruction by exact measurement, very accurate, and even with some noise, we can still tell them apart. So for most difficult case, there are 4 different obstacles separated from each other as inhomogeneity. Our reconstruction works well and stable. So that is the end of my talk, and I'd like to say thank you to my supervisor, Junzo, and also the faculty, the department, for their support in my PhD study. Thanks for your time and listening. Questions are welcome.
Thank you, Ms. Liang. So for the audience from the Zoom, you may type your question in the chat room. And is there any question from the audience at the venue? All right, we received one question in the chat room. What are the main advantages of WGM?
So first, with Galerkin method, it is a non-conforming finite element method, and it is by, there has been some work that indicated that the Galerkin method is very similar to discontinuous Galerkin method. And I'm not very expert in this domain, but in our problem, EIT problem, it is needed to use such kind of non-conforming method, as it is the setting would, like this. When we attach those electrodes, there will be some discontinuity of the true solution around the surface, as there will be a thin layer force forming around between this electrode and the conduct and the object itself. And in this case, it is important to find a more accurate method than just the traditional conforming finite element method. And that's my answer.
Professor Song?
Thank you. I have a follow-up question. It's called the Galerkin method.
Yeah.
So is this a person called Galerkin who invented this method initially?
Galerkin invented the finite element method, I think. Yeah.
Okay. So the word weak Galerkin meaning what? Meaning this is applicable to the field where the signal is weak?
Weak means that in the setup of this method, like here, the traditional with the differential operator here would become this operator. It is defined in a larger space than the continuous space. And therefore, it is mathematically a weaker definition than the partial differential operator.
Okay. Thank you.
Thank you.